Patty's Calculus Videos, written and performed by me, Patty Leitner.
Part 2, Derivatives. Section 3.4, the chain rule.
Lesson 1, the chain rule and the general power rule. Part 2.
I want to make a remark. When I use the chain rule, I just think chain rule each time. I think derivative of the outer evaluated at the inner times derivative of the inner. But there is a special case that leads to a special rule in the circumstance where your outer function is a power function. So when the outer function is a power function, such as x to the n, where n is any real number, then the derivative of g of x to the nth, we can use the chain rule on this and get sort of a special case of the chain rule, which is referred to as the general power rule. You might remember that the original power rule is just the rule that says the derivative of just x to the n is nx to the n minus 1. And this would be the general power rule, where instead of just having an x to the nth power, we have a whole function of x, namely g of x, raised to the nth power. And if you think about the chain rule up above here, derivative of the outer evaluated at the inner times derivative of the inner function, we can develop this side of this special case of the chain rule where the outer function happens to be a power function, rather than something like here the outer function was an exponential function, or on some of our earlier examples, I think on the last page, the top example, we had a sine x function as our outer function. So this is only in the case where the outer function is something to the nth power. And yeah, I can see clearly that here is my inner function, this is my g of x, and then the outer function, the f of x in this case, I wrote it with empty parentheses, the outer function would be something to the nth power. That's what we'd be thinking in our little cloud. Well, what happens when I take the derivative of something to the nth power? I pull down the n. So when I take the derivative of the outer, I would pull down the n, and it would be evaluated wherever I want, so it's n times whatever, and then this would be raised to one lower power. So I pull down the n, one lower power would be n minus 1. So n times whatever I plug in raised to one lower power, the n minus first power. And that's just writing the derivative of my power function with empty parentheses. N times whatever to one lower power. So that's the derivative of the outer function. We want to evaluate it at the inner function. So I found derivative of the outer. Now I'm going to evaluate that at the inner. We don't have a specific function for g of x, so I'm just going to put g of x inside here. And that's the first factor in my chain rule. It's derivative of the outer evaluated at the inner. But don't forget, by the chain rule, I have to multiply by the derivative of this inner function. Well, what is the derivative of that inner function? Well, we don't know what g is, so in general, I would just write times g prime of x. This gives us a really nice shortcut rule that allows us to find the derivative of any function of x raised to any constant real number. And it says, I'm going to kind of rewrite this in purple, it says that the derivative of a function of x raised to the nth power, we pull down the n, we do that function of x to one lower power. So at this point it's very much like the power rule that says derivative of x to the n is nx to the n minus 1, except that the chain rule says you have to remember to also multiply by g prime of x. So that's what's referred to as the general power rule. I tend to just think of it as the chain rule, and it's really a special case of the chain rule where the outer function is a power function, something to a constant power. If you thought about the two examples that we did on this page, can you tell me which one of these we could apply the general power rule to? In other words, which one of these has an outer function that is a power function? Well, if you look at this one, it does have an outer function that's a power function. It's something to a constant, something to the fourth power. So this one we could have used the general power rule on. We could have said, oh, if I want the derivative of x to the fifth plus e to the x raised to the fourth, I could use the general power rule that we just wrote out, where my n in this case is just equal to 4. So as long as it's something raised to a constant power, we can use the general power rule. Well, what would the general power rule say then? It would say, I pull down my power, so I pull down the 4, and then I'm going to have whatever my inner function is, and I can see the inner function is this, x to the fifth plus e to the x, raised to one lower power. So 4 minus 1 would be the third power. So that's derivative of the outer evaluated at the inner, if we were thinking of it in terms of the chain rule. And the power rule says then don't forget to multiply by derivative of the inner. So I would still have to multiply by derivative of this inner function. So I would still have to multiply by, let's see, derivative of x to the fifth would be 5x to the fourth plus derivative of e to the x. It's its own derivative, so I get e to the x. So you notice that I actually end up getting exactly the same answer that I did up here. Well, let's look at it right at this stage. I get exactly the same answer that I got here using the chain rule. Sometimes people find this a little bit easier to remember, the general power rule. Pull down the power, do your inner function to one lower number, and then multiply by derivative of the inner function. However, I want to stress that the general power rule does not work on every example. Think about the top example. Is the outer function a power function? Unfortunately, it is not. Remember that a power function is something of this form, x to the n, where n is the constant and the variable is down in the base. This is not a power function. The base is a constant. Remember, e is about 2.718, so it's a specific number, and the variable is up in the exponent. So just notice this is an exponential function when the variable is in the exponent. This is a power function when you have a constant up in the exponent. Okay, well, let's go ahead and do a couple more examples using the chain rule and or the general power rule. All right, so let's see what we have next. At the top of the next page, I have this problem to do. I'm asked to find the derivative of the square root of x cubed minus 2x minus 1. Well, again, it's probably a good idea to rewrite before you take the derivative, because what do we really mean by that square root? It would be nice to write it with an exponent instead, and the square root of something is the same as raising that something to the 1/2 power. So this would be the same as x cubed minus 2x minus 1, all raised to the 1/2 power. That makes it a little easier to see that the outer function is something raised to a constant number. So I want to ask you this question: could we use the general power rule in this case, that special case of the chain rule? And yes, we could, because the exponent is a fixed constant number. So that is a power function. Let's go ahead and identify our inner and our outer function, and it'll make it a little easier to see my answer to that question. My inner function is what's inside the parentheses, so that's my g of x is x cubed minus 2x minus 1. If that's my inner function, the outer function, and again I'm going to write it just with empty parentheses, f of whatever I throw in must be whatever I throw in to the 1/2 power. I'll write it as empty parentheses raised to the 1/2 power. And again, we're kind of just thinking this in our heads, and you don't necessarily have to write it down. But then f of my g of x would be g of x to the 1/2, so that would be x cubed minus 2x minus 1 to the 1/2. So when I check in my mind f of g of x, it does give me the function that was given here to differentiate. And yes, I could use the general power rule. And what's my n in this case? My n is the number 1/2. So you can either think general power rule, or you can think chain rule. The chain rule works in all circumstances, whether the outer function is a power function or not. So I tend to like to use the chain rule in all cases. But if you like the general power rule, that is fine to do it that way. I'm going to go ahead and just think chain rule because it works in every circumstance, whether it's a power function for the outer function or not. And I just think, gee, I'm trying to take the derivative of the x to the 1/2 function. When I take that derivative of the outer function and I find f prime, I pull down the 1/2 and it's going to be evaluated at whatever I'm plugging into my derivative of the outer, and then I have to raise this to one lower power. So remember that if I had f of x equals x to the 1/2 and asked you to find the derivative, you'd say, oh, okay, f prime of x is 1/2 x, and it'll be to one lower power, so I have to do 1/2 minus 1. That would be x 1/2 minus 1 would be negative 1/2. So f prime of whatever I plug in is 1/2 times whatever I plug in raised to the negative 1/2. And again, this stuff, write it down if you're not sure, but pretty soon you probably can think all of this in your head. So I pull down the 1/2, I'm taking the derivative of this outer function. I do whatever I'm plugging in to one lower power, so I do 1/2 minus 1 is negative 1/2. That's the derivative of my outer function. I want to evaluate that at my inner function, and g of x is this thing, x cubed minus 2x minus 1. So that's derivative of the outer, evaluated at the inner, and then I just have to remember to multiply by derivative of this inner function, and the derivative of the inner function, let's see, would be 3x squared. That's the derivative of x cubed. Derivative of minus 2x would be minus 2, and derivative of the constant negative 1 would just be 0. So derivative of the outer, evaluated at the inner, times derivative of the inner. And remember, we could have done this using the general power rule as well, and the general power rule would just say, this is my n, I pull down the n, I do my g of x to one lower power, and 1/2 minus 1 would be negative 1/2, and then I multiply by derivative of my inner function. So it will give you exactly the same result. Now usually we will pull all this together and rewrite it a little bit, so let's do that to kind of neaten it up. Normally we put this shorter factor in front, so I'd write it as 1/2 times 3x squared minus 2, and then I'd multiply that by this other factor, and I notice that this other factor has a negative exponent. My final answer shouldn't include any negative exponents, so I want to rewrite it as an equivalent expression with a positive exponent. So for this factor, all this stuff raised to the negative 1/2, I want to write that as 1 over all of that stuff, x cubed minus 2x minus 1, but now raised to the positive 1/2 power. So this term, this factor right here, becomes 1 over x cubed minus 2x minus 1, but now raised to the positive 1/2. Usually we don't leave it as a string of factors like this. If we can multiply them together and write it as a single fraction, we do so. So remember that you could think of this 3x squared minus 2 as being over a 1. If we multiply all of these numerators together, I will just get 1 times this factor times 1. That would just be that factor. So I would get 3x squared minus 2 in the top. In the bottom, I have 2 times 1 would be 2. And then I have all of this stuff raised to the 1/2. You could leave it with that fractional exponent there, but I noticed that my original problem was written with a root rather than a fractional exponent. The tradition is that if the original problem is written using a root symbol rather than a fractional exponent, we write our answer with a root symbol instead of a fractional exponent. So all of this stuff raised to the 1/2, remember, would be the same thing as the square root of this stuff. So I could write this as square root of x cubed minus 2x minus 1. That would be the slightly preferred way to write our answer rather than leaving this fractional exponent down in the bottom. So the top becomes the 3x squared minus 2. The 2 here out in front came because I had a 1/2, so I had a 2 in the denominator times 1 gave me 2. And this stuff to the 1/2, same thing as the square root of that stuff. Okay, I'd like you to go ahead and think about the next example. So pause the tape, give that a try, and then we'll go ahead and do it together. Okay, so for this one, I just want to again identify what the inner and the outer function is. It's tangent of a whole bunch of stuff. And notice in particular, it is not the function tangent x times the function 5x squared plus 3x plus 1. That is not the problem that I'm given. It's not a product of two functions, so we do not use the product rule here. Notice that 5x squared plus 3x plus 1 is inside the tangent function. There's no x here. So it is not a product of tangent x and this polynomial. It's tangent of that polynomial. In other words, the polynomial is inside the tangent function. So what does that mean? It means that my g of x is this thing, the thing that is inside the tangent function. So let's go ahead now and see if we can decide what the outer function is. If this is my inner function, the outer function must be f of whatever I'm plugging in is tangent of whatever I'm plugging in. So that is my outer function in this case. And I can certainly see that if I do f of g of x, I'd get tangent of g of x, and g of x is exactly this polynomial that we have written inside. So first of all, let me ask you, could I use the general power rule in this case? Unfortunately, our outer function is not a power function. It's the tangent function. It's a trig function. So I can't use the general power rule to do this, and that's why I prefer to just think chain rule so that I only have to memorize one rule. I don't have a great memory, so I like to memorize as few rules as I possibly can. So let's go ahead and write down, we do have to use the chain rule in this case, so I'm going to be doing the derivative of the outer evaluated at the inner times the derivative of my inner function. So now I have to think, well, what is the derivative of my outer function? And the derivative of tangent x, you may remember, is secant squared x. So the derivative of the outer is going to be f prime of x, or whatever I plug in. Derivative of the outer is secant squared of x, or in general, secant squared of whatever I plug into my derivative. So the derivative of the outer is secant squared of whatever I'm plugging in. So that's the derivative of the outer function. And remember again that this exponent that I've written in here is really a shorthand notation. It's used only with trig functions, but it really means secant of whatever the whole quantity squared. But in this case, since we've already found the derivative, we don't have to worry about rewriting it in a long notation. So I've taken the derivative of the outer, that's secant squared. I'm supposed to evaluate that at this inner function. So the thing that goes inside here is my g of x, and that would be exactly 5x squared plus 3x plus 1. So I've done derivative of the outer, and I've evaluated it at the original inner function. Now, according to the chain rule, I'm supposed to multiply by derivative of the inner function. So now I have to multiply by g prime, so I'm taking the derivative of this inner function. Derivative of 5x squared would just be 10x, and derivative of 3x would be 3. Derivative of 1 is just 0, since it's the derivative of a constant. Again, it's traditional to pull polynomial factors to the front of trig or exponential functions. So usually the final answer where we would reverse the order of these factors and write the 10x plus 3 factor first times secant squared of 5x squared plus 3x plus 1. And that's how we would write our final answer. I believe the reason that polynomials are usually written first instead of leaving it in the order that we had it up here is that it's very clear then that the 10x plus 3 is not inside the secant squared function, that it's 10x plus 3 times secant squared, and the only thing that's inside is the 5x squared plus 3x plus 1. And that's why we usually pull those polynomial factors to the front. It's just a little bit clearer. Okay, the next thing we're going to talk about is doing some examples that require more than one rule, more than the chain rule. So all of the examples we'll be looking at next will involve both chain rule and a second rule, such as the product rule or the quotient rule or something like that. In order to do these kinds of examples, we will have to think about what rules will be needed, and we'll also talk about what we will think of as the overall rule, and that would be the rule that we're going to end up applying first. Okay, well, let's look at a specific example here. Here I'm asked to find the derivative of x over x plus 5, so it's this fractional expression, all raised to the 4th power. So I have to think about what rules I'm going to encounter as I start to take the derivative of all of this. Well, I notice that I have some function of x, namely x over x plus 5, this thing that's inside, all raised to the 4th power. So I do have an inner function and I have an outer function. That means that one of the rules I'm going to need is the chain rule. I've got a composition of two functions, an inside function all raised to the 4th, that's my outer function, so I know I'm going to need the chain rule. And in fact, I would think of that as what I'm going to call the overall rule. And by that, I mean that's kind of the overall thing that's happening. I have an inner function all raised to the 4th, so I have an inner function and an outer function. The overall expression is a composition of two functions. So yeah, we would go ahead and we would apply the chain rule, take derivative of the outer, evaluate at the inner, then times the derivative of the inner function. But notice that when I take the derivative of the inner function, which is part of what we would end up doing in the chain rule, when I take the derivative of x over x plus 5, what rule am I going to have to use to do that? Well, that is a quotient. So somewhere along the line, I'm also going to need the quotient rule. Now, if you want, you can just notice maybe at first that I need the chain rule. I have an inner function and an outer function, so I know I need the chain rule. And if you didn't notice right away that you're going to need the quotient rule somewhere along the way, I think you'll figure that out as you go. So the most important thing is to kind of think, what's the overall thing that's happening? The overall thing is a composition of an inner function and an outer function. So the overall rule that I'm going to use is the chain rule. And somewhere along the way, when I take the derivative of the inner function, I will also need the quotient rule. And as you get more practice, you'll get better at deciding what the main thing that's happening is and what the overall rule you're going to need is and what the maybe lesser rule is that you'll need somewhere along the way to complete your process. Well, let's go ahead now and attack it exactly the way we did all of our other examples. I'm going to go ahead and decide, well, What's my inner function? My inner function is this thing. That's what's inside the parentheses, and so that's my g of x in this case, x over x plus 5. If I make that my inner function, I have to think in my mind, well, what's my outer function? My outer function, since all of this is raised to the 4th power, would be the x to the 4th function. If I write that with empty parentheses, I would say f of whatever I'm plugging in is going to be whatever I'm plugging into the 4th power. So again, that's just kind of in a cloud in my mind. I'm thinking my outer function is whatever raised to the 4th power. And I can see that if I do f of g of x, I would have g of x to the 4th, and that would be exactly x over x plus 5. That's what g of x is, raised to the 4th. So I've correctly identified my inner and my outer function. Now let's go ahead and use the chain rule. So the chain rule says I'm going to be doing the derivative of the outer, evaluated at the inner function, and I'm going to be multiplying that by the derivative of the inner function. So let's go ahead and find the derivative of the outer. Well, the outer function is the x to the 4th function. So to take the derivative of the outer with empty parentheses, I simply pull down the 4, and I'm going to have whatever thing I'm evaluating that at to one lower power, so to the 3rd power. So here I've taken derivative of the outer is 4 times whatever I decide to plug in to the 3rd. Well, what am I supposed to plug in? I'm supposed to plug in g of x, and g of x is this fractional expression, x over x plus 5. So far, we've done the first factor in the chain rule. I did derivative of the outer, evaluated the inner. Great. Now I'm supposed to multiply by g prime of x. So I'm supposed to be multiplying by the derivative of the inner function. But I notice when I look at the inner function, that's going to be a little tougher in this case because the inner function happens to be a quotient, and so I'm going to have to use the quotient rule in order to find its derivative. What I usually do in problems like this is I do the problem in 2 steps. And I strongly advise you to do the same thing, especially as you're learning to apply multiple rules, such as the chain rule, plus we've now discovered we're going to need the quotient rule. If you try to do everything in one step, you will find that you kind of get mixed up because you're sort of applying one rule and then you're applying another rule, and usually students get things in the wrong place because they're trying to do too much in one step. So I strongly advise you follow the following procedure. It also makes it more clear for other people that are looking at your work, or for yourself if you're going back and checking your work, if you don't do too much all in one step. So this is the way I do it. I say, okay, I've done derivative of the outer, evaluated the inner. Oh, but now I see when I do the derivative of the inner, it's going to involve another rule other than the chain rule, namely the quotient rule. So I write it this way. I say, well, I'm going to do that derivative in the next step, and I'm going to use my handy operator notation to say I still have to do the derivative of the inner function. And what is the inner function? The inner function is this thing, x over x plus 5. I'm not really done taking derivatives yet because I haven't done the derivative of the inner function yet, but I'm leaving that for the next step. That way in this step, the only thing that I've really done is the chain rule. That's the only rule that I've applied. I've done derivative of the outer, evaluated the inner, and I've just written times the derivative of the inner. The derivative of, using this operator notation, and here's my original inner function. And I leave that derivative of the inner until the following step. Okay, so let's see now how we would do the quotient rule in the following step. So this part's all done. It's the derivative of the outer, evaluated at the inner. We finished that part. But this operator says I still have work to do. I'm still supposed to take the derivative of this expression, and that is where I will need my second rule. That is where I will need the quotient rule, because I notice that the inner function is a quotient. Okay, let's see if we can remember how to do the quotient rule. And if you want to, you can use the low d high method that we talked about, or you can simply use the f prime times g minus g times f prime, all divided by g squared, whichever way you learn the quotient rule. I kind of like the jingle, So I'm going to remind you about the jingle for the quotient rule. So over here on the side, just to remind you of that little jingle that helps us to remember the quotient rule, if we're taking the derivative of what we call the high function over the low function, and I kind of abbreviate high and low as hi over lo, the derivative, and the jingle is meant to rhyme, says that we do low d high minus high d low, square the low, and away we go. And if you get these terms in the top in the wrong order, the jingle doesn't rhyme. So low d high means do the lower function times derivative of the higher function, minus high d low, that means do the higher function times derivative of the lower function. And then remember that you have a g squared in the bottom, so you have the lower function squared. If you re-identify these things as an f over a g, just keep in mind that your f and your g mean something different than in the first step where we were applying the chain rule and we were identifying the outer function and the inner function. That's another reason it's kind of nice to use this little jingle that I have over here to find the derivative rather than having to use another f and a g in this second rule that we're applying, the quotient rule. So let's see if we can go ahead and find this derivative. I'm supposed to do the lower function times derivative of the higher function. The lower function is x plus 5, and I multiply by derivative of the higher function. It's a little hard to see because I wrote the f here. The higher function is x, and derivative of x would just be 1. Then I subtract off the higher function times derivative of the lower function. So the original higher function is x, and I multiply by derivative of the lower function. The derivative of x plus 5 would just be 1 plus 0, or 1. And then I divide the whole thing by the lower function squared. So I'm going to divide by the original lower function, x plus 5, quantity squared. So this is just applying the quotient rule to this inner function. It's the bottom function times derivative of the top minus the top function times derivative of the bottom divided by the bottom function squared. And the rest of the problem is just trying to clean all of this up algebraically. But at this point, we are actually done taking derivatives. So we applied the chain rule first, did derivative of the outer, evaluated the inner, times the derivative of the inner, but we saw that derivative of the inner was going to involve a second rule, the quotient rule, and so we waited and did that till the next step. So that way I'm not using two rules in one single step. I'm separating those two processes, and it's really quite a bit easier in a complicated problem like this to do the whole thing with one rule for one line of calculations and then wait until the next line of calculations to apply your second rule. All right, let's try to just clean this up a little bit. This is just my slide number right here, so ignore that. So let's see what I've got. I'm going to rewrite this way. This is 4. You notice that this is x over x plus 5, that fraction cubed. That'd be the same as cubing the top and the bottom separately. And I'm going to write it that way. I'll show you why in a moment. So I'm going to write that as x cubed over my denominator, x plus 5 quantity cubed. And let's see, this numerator, if I multiply it out, it looks like I'll have x plus 5 minus x. Those x's are going to drop out, and I'll be left with just 5 in the numerator. So I'll have an x plus 5 minus x, the x's drop out, and I'm left with just a 5 in the top. And then down in the bottom, I still have this x plus 5 squared. So this numerator simplifies quite a lot just to the number 5. Well, let's try to rewrite things by pulling factors together. Remember, this is really a 4 over 1, so you can think of the 4 as being in the numerator. And if I multiply all the numerators together, I have 4 times x cubed times 5. That would be 20x cubed in the top. And in the bottom, I have x plus 5 cubed times the same base, x plus 5 squared. Remember, when you multiply like bases, you're supposed to add the exponents. So it would be x plus 5 raised to the 3 plus 2. You have 5 factors of x plus 5 there. So it would be x plus 5 to the 5th. And that would be the simplest form for my final answer. All right, let's go ahead and go to the next page and see if you can do a problem on your own, and it will be a problem that involves more than one rule. So I want you to think about this problem. You're asked to find the derivative of x cubed times sine of 5x minus 1. Try to think about what the overall rule is that you're going to be using. In other words, what the overall structure of this problem is, and that'll determine what rule of differentiation you need to begin to attack this. And then if you can think of what the overall rule is, think of whatever other rule you might need along the way might be. So try to think about those two things first, then maybe restart the tape, be sure that you've thought about it correctly, and then we will have you pause the video again and actually go ahead and do the calculations for the derivatives. So take about 30 seconds, try to identify the overall rule that you'll be using, differentiating this function, and then think about whether there will be any other rule that will be needed to complete the differentiation.